In the present video, we're going to talk about using the probability distribution functions available in the statistical tool plugin to obtain critical values for statistical inference distributions. We're going to start by looking at this SMA Studio file. If we treat the mean value of a sample of size n as a random variable x bar, the expected value of that random variable is the mean value of a population from which the sample comes from. It turns out that if the mean has a size greater than 30, which is known as a large sample, we can define a standardized variable z equal to the random variable x bar, which is the mean of the sample minus the mean of the population, divided by the standard deviation of the population divided by the square root of the number size, the size of the square root of the size of the population, sorry. And that variable follows the standard normal distribution. That's a normal distribution with zero mean and standard deviation equal 1. And we can use then this distribution to find critical values for the statistic z. If evaluating x bar, we use a small sample which requires n to be less than 30. There's another standardized variable called t that is very similar to the other one, except that we use the standard deviation of the sample in the denominator. This will follow what is called the student's t distribution with a parameter equal to n minus 1, the size minus 1. This parameter is given the symbol nu and is referred to as the degrees of freedom of the distribution. If we analyze the variance of the sample a squared, the expected value is equal to the variance of the population. We can form a parameter called chi-square equal to n minus 1, multiplying the variance of the sample divided by the expected value of the variance of the population. And that will follow a distribution called chi-square with a parameter nu that, in the case of similar to the case of the student distribution, is equal to n minus 1, and it represents the degrees of freedom of the random variable or of the distribution. Finally, when we compare two samples, the ratio of the sample variances to the population variances for the two samples forms a statistical and called F, with parameters nu1 and nu2 equal to the sample size minus 1 for the one sample, so sample size 2 minus 1 for the second sample. And this parameter follows the so-called F distribution with parameters nu1 and nu2. And these four the probability distributions are used for statistical inference, specifically to determine confidence intervals and hypothesis testing on the mean and the variance of samples. The critical values. The critical values of this distribution are such that the probability of z being less than minus z sub a alpha is equal to alpha, where alpha is called the significance level and takes typical values of 0.01, 0.05, and 0.10. And so we can define these probability calculations based on the level of confidence alpha to determine the critical values minus z sub alpha, or z sub alpha over 2. For significant levels of 0.10, 0.05, and 0.01, we have equivalent confidence levels of 90, 95, and 99%. The relationship between C and alpha is given by this expression. And the normal distribution, the standard normal distribution, has a probability density function, which is given like this. Or if you use the statistical tool package, you can obtain it this way. And when we plot this distribution, we find it's a symmetric curve about 0, and it's called the Gaussian bell or the Gaussian curve, and we're going to use it to obtain critical values. Critical values, for example, we have one-sided lower tail. We're looking for an value minus z sub a, so that the probability to the left is equal to alpha, z sub alpha actually, not z sub a, or that the probability of the z is greater than that z sub alpha is equal to alpha. And if we split in symmetric positions the probability alpha into alpha over 2 to the right, alpha over 2 of the left, of these values, they turn out to be negative with each other. Given a confidence interval, then, a significance level corresponding to this confidence interval, for example, 0.10 with confidence of 90%, the value of z sub a, negative here, will be obtained as the normal whose probability to the left is alpha, or we can get it as the normal whose probability to the right is 1 minus alpha, except that there will be the negative of the other. We're talking about this value, this negative value here, or this positive value in the middle figure. If we want to find the z sub alpha over 2, we just look at the fact that the probability to the right is 1 minus alpha over 2. For this case, the probability to the right is alpha over 2. The probability to the left is 1 minus alpha over 2. And this is how, given a value of alpha, you will calculate the critical value of z sub a for the one side lower tail, one side upper tail, two-sided upper tail. This applies, as I mentioned before, to large samples n greater than or equal to 30, and can be used for determining confidence intervals or for hypothesis testing on the mean of a sample, the difference of means of two samples, a proportion of a sample, and the difference of proportions of a sample. Regarding the student t distribution, the statistical tool plugin has a reference to it, PDF to t of t new, but it doesn't have a closed form expression. I don't understand why, because it's not that complicated, but they don't. The fact is, though, that you can plot it, and when you plot it, there you go. For different values, as I show here, close the display input data, you get that symmetric shape, and it turns out that as nu grows, the student t distribution is getting closer and closer to the standard normal. So the value of 30 is kind of a limit. Below 30, you have small samples, you use student t. After 30 elements, you use this standard normal distribution. The picture of the critical values for the t distribution is similar to the z distribution. And so we're going to show you here the calculations will be very similar to the case of the z distribution. For a given value of alpha, that's the significant level, corresponding to a confidence level, for example, for 0.10 is 90%, and determining or showing or using the degrees of freedom, we can calculate a t sub alpha, will be this case here, which is negative, when the probability to the left is alpha, or this value when the probability to the right is alpha, or the probability to the left is 1 minus alpha. And to obtain the t sub alpha over 2, we use the inverse cumulative distribution function of t when the probability to the left is 1 minus alpha over 2. So these formulas, you can just borrow them and use them to calculate your critical values for the t distribution and these for the z distribution. You can change the values of alpha and obtain the corresponding values. If we change here, for example, to 0.01, we will obtain the proper results. As in the case for the large samples, when you have a small sample, the student t distribution can be used for determining confidence intervals and hypothesis testing on the mean of a sample, the difference of means of two samples, a proportion of a sample, and the difference of proportions of a sample. With this, we're going to end this video, this part one, and we're going to work in part two with the other two distributions.